So let's answer this question at the bottom. It says choose the most stable conformation. Which one is the most stable?
One in the middle.
This one,
Yes.
right? That's because the methyl groups are as far apart as they can be from one another. All right. And then which one is the least stable?
The third one.
This one. Right. This is 19 kilojoules per mole. This one is roughly 0 kilojoules per mole. And then this one will be 3.8, right? Because that's the only interaction present is that gauche interaction right there. All right. Let's walk through a couple of these up here, the other two, and then we're gonna start talking about these chair conformations. So again, with that Newman projection is really important to understand with the Newman is that these carbons, this is a carbon right here, and the circle behind it is also a carbon, right? So we're going to count these carbons. Let's count them up. 1, 2, 3, and then the circle behind it is a carbon. That's 4, 5, 6, 7. So 7 carbons total, right? So what would that look like as a in a skeletal form? As just like a straight chain. Because there's no other substituents on there. If we counted 7 carbons, what would the skeletal form look like? And there are no substituents.
Would it just be a simple chain?
It would just be a 7-membered chain like so. Right. And you can see that's 1, 2, 3, 4, 5, 6. How can I miss that? 7. All right. Let's do the other one. Again, the Newman projection, that's 2 carbons out of the chain, right? So this is a carbon, that's a carbon, and then 1, 2, 3, like so. What would that look like? So 1, 2, 3, 4, a 5 carbon chain. Is that right?
Yes.
Yes.
Yeah. Bromine on the first, carbon on the fourth.
Good, excellent. The bromine right here. And then if that's carbon 1, and the back carbon is carbon 2, that's 3, 4, 5. So you got a bromine on carbon 1. And then a fluorine where?
The fourth one.
Carbon 4. Like that. How we name that? Anybody?
Would it be
Would it be-
1 bromo, 4 fluoro, pentane?
Yep. Good. Pentane is the parent, 5 carbon chain. You got a substituent on carbon 1 and carbon 4, and you list the substituents in alphabetical order. So B comes before F. So it's 1 bromo, 4 fluoro, pentane. All right. Now let's get into the chairs. I gotta add a page because well actually I'm gonna cut this right here and add it to another page. So I don't want to talk about the disubstituted rings. I want to talk about monosubstituted rings first. And then we'll talk about disubstituted rings. So before we even talk about conformational mobility, the chair, the 6-member ring is probably that's sloppy looking. The most stable of your cyclic systems, right? And you can actually think about the 6-member ring. If we look at this from a Newman perspective, we're going to look at these 2 carbons and we're going to look at these 2 carbons. And so I could actually draw this out like this. Right, where this is carbon and that's a carbon. Let me fix that up. So these are hydrogens here. And on those back carbons, those are hydrogens as well, right? So this is what a Newman projection, if you drew the 6-member ring in terms of showing it as a Newman projection, this is what it would look like. And the reason why the 6-member ring is so stable is because of the dihedral angle between those hydrogens on the ring. It's like, I think it's 10, I want to say it's 109.5 or 0.4. Right, so the angles between those hydrogens, they give that ring stability because you don't have a lot of eclipsing interactions, right? And so that ring is going to adopt, the 6-member ring is going to adopt like the most stable conformation. So a lot of times you see a 6-member ring written like a hexagon, but in reality, it's actually written, it actually exists as a, what we call a chair. Same 6 carbons, 1, 2, 3, 4, 5, 6. So this is a chair. It could also exist as a boat, but the boat is much less stable. You can see why it's called a chair and a boat, right? It's kind of goofy, but the chair has basically an outline here of a lawn chair. If you watched that video, you saw that. So basically got an outline of a lawn chair or beach chair. And then the boat basically has an outline of a boat. But the boat is much less stable. It does exist. There are certain reactions and certain transition states that occur when you are doing cyclic molecules, or you have like a cyclic transition state. It may actually go through a boat for one reason or another, but the chair is always going to be your most stable. So on the chair, if I were to put the hydrogens in, each carbon on the chair has 2 hydrogens, right? Somebody tell me what the hydrogens that are pointed vertically, what position is that if it's pointed in a vertical direction?
Is it apical?
Axial, good. So the ones that are pointed vertically like this, these are axial. And vertical is not just up, it can be down as well, which we'll see in a minute. And then the ones pointed horizontally, let me change the color of that. The horizontal hydrogens here, these are equatorial. And if you watch the video that I sent, it basically described them as forming an equator around the 6-member ring, right? So they kind of jut out from the ring. right? And this is, again, when you think about the 6-member ring and its 3D conformation, this is what it looks like. Because when we draw it like this, that's in 2D. All right. So then there's another axial or another site right here. Right, which has a axial hydrogen, like so. All right, and then, so this is the top face. And that's very important to understand that these chairs have, it's like a surface. You have a top surface and a bottom surface. On the bottom surface, we can put those hydrogens in too. I'm gonna draw them in a different color. So this is gonna be axial, that's axial, and that's axial, right? Because every one of the carbons has to have 2 hydrogens on it. And then the equatorial ones, I'm going to leave in black. So this is going to be equatorial. That's equatorial. And then that's equatorial. So you got 3 axial sites on the top face, 3 on the bottom face. And let me fix this. So this hydrogen back here is actually going behind that line, right? That's shown. So I don't want you to confuse that and think it's somehow overlapping with it. It's just behind it. All right. Normally you can show that by just making this line darker. All right. Questions about the faces, the hydrogens, the positions, right? So forth. Go ahead.
Can you go up? So when you're doing the, I guess, Newman projection for that, for the ring, I'm not understanding how, I don't see like the 6 carbons.
Yeah, so this is 1, right? So that's 3. And then the big circle is also a carbon. I mean, so that's 4, 5, and then there's a carbon back here, that's 6. So what you're really doing is taking this ring and laying it flat so that you're seeing it from like this. If this is the plane, that's how you're looking at that ring, like basically looking at it down this carbon right here.
Okay.
Yeah, but it's flat. Imagine it sitting on your desktop, right? Like your phone or your laptop or whatever. It's sitting flat like that, and you're looking at it from that perspective. That's how you're able to generate that Newman projection.
Okay. And then for the chair confirmation, like I understand that the hydrogens are the ones that are vertical or axial and the ones on the side are equatorial, but I guess the hydrogen that's I guess the second one on the second carbon, the one that's black highlighted. How is, you said that's equatorial? I don't understand how that is.
The one that's in blue?
The second on the where top face. Near the top face. The one next to the green hydrogen. That's not highlighted.
Oh, this one. You're talking about this
Yes.
one?
Yes.
Yeah. So let me draw that a little bit better. So that actually should be a little bit more at angle. So it's here. It's not vertical, like it's actually jutting out from the ring, just based on the geometry of each carbon, because every carbon in that ring is still a tetrahedron. So that hydrogen it's at a little bit more of an angle than what I had initially drawn.
Okay.
Right, but it's definitely not vertical. It's pointed out like toward the back of the paper.
Okay, and same with the one, I guess, on the bottom.
It's
like too. Okay. Thank you.
So on the chair, the axial positions and the equatorial positions, if I were to take that chair and do what's called a chair flip, which is what chairs do when they're trying to access a more stable conformation. Here, you don't need it to do a flip because there are no substituents. But I'm gonna show it anyway, just because we need to see what happens, right? And I wish I could show this in like 3D, or with a model, but we can't do that. So I'm just going to redraw it. So in a chair flip, what happens is all of your positions switch. So everything that was axial becomes equatorial. Everything that's equatorial becomes axial. So I'm going to take that bottom, the back carbon. I always like to show this in terms of like these two carbons. It makes it easier to think about. So I'm going to take that front carbon and flip it up. So it's going to be pointed this way now instead of fix that. It's so sloppy.
Dr. Russell, I have a question.
Go ahead.
I'm having a hard time understanding the 1-3 diaxial relationship.
Oh, we haven't got to that yet, but I'm going to explain it. I'm just showing now just the conformation part. And then when we put a substituent on, we'll talk about the diaxial stuff. All right, so this carbon, let me circle it, is now pointed up. And then the back carbon that was circled in red is now here. So all of those, let me put the axial positions back in, because all of those would have been your equatorial hydrogen. So here, and then here. On the bottom face, it's the same. Yeah, they all in black. Here, here. Make that a little bolder. And then here. Right, so all those equatorial hydrogens that were in black on the top molecule, right here, here, right, all of those are now axial when I do the ring flip. And then the ones that were axial are now going to be equatorial. So this is that's equatorial. And then this is, that's equatorial. And this is also equatorial like that. And then on the other carbons, this is equatorial here. This one is equatorial, and then so is this one. And those are the ones that were highlighted and highlighted in green. So all of your axial sites or hydrogens, when you do the ring flip, become equatorial. All of your equatorial hydrogens, when you do the ring flip, become axial. And you can see that. So a ring flip is basically you contort or flex the ring, right? Not you, but the ring does it on its own for the sake of energetics. right? So that's what we get the term conformational mobility from, right? This ring can adopt different conformations so that you're able to get out of a bad conformation or a high energy conformation. Right, and you can look up top, it's the same, right? We had a R group here that was axial, and then over here we did a ring flip to make that R group equatorial. So we don't, this really doesn't matter until we start putting substituents on the ring. So let me add a page and we'll talk about that. We're going to start out talking about monosubstituting. Right, and so all that means is that I'm going to put one substituent on the ring. So if I have a ring like this, let's start out by just putting a methyl group on the ring, right? So obviously this ring has two different conformations that it can adopt. It can have a conformation where the methyl group is axial. I'll do that here. So this is axial, that's equatorial, right? And then you got, I'm just going to put in the axial hydrogens because these are the ones that make all the ruckus. Right? So that's one conformation. And then if I did a ring flip, and I'm going to show this as an equilibrium because that's actually what's happening. Right? I'll show this as an equilibrium. And if I did a ring flip, I would have this as my new chair, right? Because this carbon is going to get pushed up. This one's going to get pushed down like that. So now the hydrogen is axial. And then the methyl group is now equatorial, right? Just a cursory understanding of this. When groups are axial, that's bad, right? Anything other than hydrogen being axial is bad. So this methyl group over here being axial is not good because what happens is that methyl group ends up having a steric interaction with the two other axial hydrogens on that bottom face, right? So let's think about that. Can somebody tell me, if you watched the video, how much it costs for methyl to be axial, for the methyl group to be axial? All right. So let me tell you why it's bad, and then we'll talk about the energy. All right. So that methyl group, how much is it? 3.8.
Yeah.
Okay. So that methyl group and that the axial hydrogen, let me highlight them here. Right. If you count the distance between those two groups, I can start counting here. 1, 2, 3. They're 3 carbons apart. Right. So that type of interaction, we call it a 1,3 diaxial interaction. The di part is because there are 2 axial things on that face that are interacting, and then the axial is because they are in the axial position. So 2 things in the axial position talking to one another, basically. And if you look at the other hydrogen, it's the same thing. It's the same relationship. Right there, 3 carbons apart, 1, 2, 3, like that. So that's how that you're going to have the same type of interaction with that hydrogen. And each one of them costs energy. right? For this method to be axial, this is 3.8 kilojoules per mole, and so is this one. So the total energy for this conformation is 7.6. .6 kilojoules per mole. It's a lot. All right. So if it's 7.6 kilojoules per mole, when I do the ring flip, which is what's necessary to alleviate that diaxial strain, this is what I get, and the energy goes to relatively to 0. Right? There are no, since this is now equatorial, right? It doesn't have those same interactions. Right? So this is a much lower energy conformation, and that's more than likely, let me not say more than likely. This is the conformation that's going to be more prevalent in nature, right? That chair. So when we think about this as in terms of equilibrium, the equilibrium is going to favor this way. If you recall, when we were doing pKa, talking about equilibrium and which side was favored, right? The lower energy conformation is always going to be favored if the two conformers are in equilibrium. Right, the lower energy conformer is always going to be favored. So it costs 3.8 kilojoules per mole for that methyl group to be in an axial position, and because you got two other axial sites, that interaction is multiplied by 2. So you have a total energy of 7.6 kilojoules per mole. All right, now Tia, you can ask your question.
I think I get it a little bit better. That you.
Okay. And this like you can imagine as the substituents get bigger, the energy for it to be axial, it increases, right? I think for a halogen like bromine, I think it costs like 1 kilojoule per mole or something like that. But if you put something on here like a tert-butyl group, let's go ahead and do that one.
I have a question.
Go ahead.
So I'm trying to I guess wrap my mind which like hydrogens and such are axial, which ones are equilateral. I'm still not understanding that. I understand what they are, but I understand.
So can you see the difference between this hydrogen here and the methyl group? Because every carbon is going to have an axial site and an equatorial site in that ring, right? So axial is vertical, either vertical going up, or vertical going down. It's like in this case, the methyl is pointed down. Do you see that?
Yes.
Yeah. Over here, this hydrogen is axial also, but it's pointed vertically upward.
Okay.
So all your axial sites are going to be the sites that are vertical on each carbon, and they're for a 6-member ring. There are 3 axial sites on the top and 3 on the bottom. Everything else is equatorial.
Okay.
What that means, in terms of direction, the equatorial sites are going out away from the ring, right? Not up or down, but they're pointed outward.
Right.
Mm-hmm.
Okay.
Does that make it clarified a little bit?
Yes.
If you had a model, that this would be like it would be so much easier to see. This is the one of the places in organic where a model set is I don't want to say a requirement, but it does help to kind of help you visualize things. So yeah, so if I took that methyl and made it something bigger, it's going to cost me more energy. So let's look at if I had a tert butyl on my chair, and I'm going to make it axial. All right. This is bad. This is horrible, right? Because there's an axial hydrogen here. There's another one back here. All right. So again, you're going to see that these substituents are going to be talking to each other, but not in a bad way, not in a good way. They're actually going to be fussing with each other. And that's not good. Right. And both of those hydrogens are fussing at that tert butyl group. Like, why are you here? I'm really not. I'm making this humanizing it to help you understand it. Right. So they're talking to each other, and it costs 11 kilojoules per mole for that tert butyl to be axial. And that's going to be it's going to cost that twice because you got two hydrogens that are axial along with it. Because again, on each face, there's the 3 axial sites. Right. So if any one of those axial sites is substituted with another atom, it's going to increase the energy of that molecule overall. Right. And then let me put in the equatorial hydrogen here. Right. Going out away from the ring. All right. So what would I do? What can I do there? What would the chair flip look like?
It would have the substituent group equatorial.
So would it look like this? That's so sloppy. I started out hot. So the new chair would look like that, where this carbon right here is going to move down this way. And then the other carbon in the front, I like to call this the front, right? This is going to move up like that. So I'm basically going to flex that ring and rotate at these 2 carbons to flex that carbon up. I'm going to rotate at these 2 carbons to flex that back carbon down. All right, so when I do that, that hydrogen that was there is going to now be axial, like so. And then the tert butyl group is now equatorial. All right, and is everybody comfortable with the fact that these are 3 CH3 groups? All right, so I don't have to draw those out. Those are 3. There's 3 methyl groups there attached to that same central carbon. And it's called a tertiary butyl group. When we abbreviate it like that. So which side do you think equilibrium is going to favor? This has a total energy of 22 kilojoules per mole, and this has a total energy of relatively 0 kilojoules per mole. If these 2 are in equilibrium, which side is going to be favored?
Right.
This side. Right. The ratio of products, which we're going to talk about how to calculate that, just not today. But the ratio of products is probably somewhere around 99.999 to 0.001. That's how bad having that terp butyl group in an axial position is. All right, questions about these monosubstituted rings. All right, I think the point I'm really just trying to get to is that once you put a substituent on the ring, you're going to increase the energy of that ring if the substituent is in an axial position. All right, so you can have axial, and then the ring, to alleviate having a group in an axial position, can do a chair flip or a ring flip to get that group in a more stable equatorial position. All right, any questions?
I have a question.
Go ahead.
So if I guess if the substituents were to decrease in size, then the energy required would decrease.
You mean as you go down in size? Yes. I didn't even finish that statement, but yeah. Yeah, so smaller atoms or functional groups, because it's not always just alkyl groups, right? You can have there's a wide variety of substituents that you can add to a ring, and the smaller groups they cost less to be in an axial position, but they still cost. It's just less. Like if I put like a halogen on here, in an axial position, I think the halogen only costs like 1 kilojoule per mole. All right, so the total energy here is going to be like somewhere in the range of 2 kilojoules per mole. And that's because halogens, even though they're like have a high atomic radius and they're big atoms, normally a carbon halogen bond is pretty long, right? So it'll be a little bit further away from the ring. Actually, let me just illustrate that instead of just saying it. All right, so that's a bad illustration, but it makes the point. So bromine, with the fact that the halogen bond is longer, the interaction between the diaxial hydrogens and that halogen is a little bit less. So that's why it doesn't cost as much for that to be axial, but it still costs. Anytime you put something in an axial site, it's going to cost, because those other two axial hydrogens are going to be upset, and yeah, it's going to be a confrontation. All right. Any other questions? All right.
What makes
So
the halogen,
go ahead.
what makes the halogen bonds, I guess, longer? Like, is it the radius? Or does
Yeah,
that,
and it's the distance, it's the actual distance from the nucleus of the electrons that are overlapping, the orbitals that are overlapping. Because it's the distance from the nucleus means those valence electrons are pretty far away from the nucleus. So that means that that bond is going to be longer because the nucleus is less accessible. Right. So when those valence electrons, those valence valence shells overlap, you're overlapping at a place on the bromine that's really far away from the nucleus, as opposed to the carbon, right? So it's a long weak bond. They're very easy to break too. That's why when you see substitution reactions and things like that, you know, the halogens are excellent leaving groups because the bonds are just not very tight, especially iodine and bromine. Fluorine is an exception because, you know, it's a small atom and the electrons are held really close to the nucleus. So those are tight bonds. So that's why you don't see those used as leaving groups as much. But yeah, it's just a consequence of where the electrons are that are overlapping. And that contributes to the atomic radius, which you mentioned. It's the more valent shells you have around the atom, or the more not valent shells, but the more shells you have around the atom, then the wider the radius is going to be, because those electrons are getting further and further and further away from the atom's nucleus. All right. Other questions? Anything else? We're gonna come back to this on Friday, and I'm gonna mention the dye-substituted ring, but I don't want to like flood you with that because I really want to talk about calculating these equilibrium ratios for monosubstituted rings, and then we'll probably just end with that instead of talking about the dye-substitute. I mean, we may do one example of a dye-substituted ring just to talk about the fact that you can have multiple steric interactions in the same ring. All right, so we're going to stop here and then we'll pick up on Friday.
I have a question.
Go ahead.
How's the test on Friday gonna be? It's just gonna be like the last exam?
Yeah.
Okay. And it's just like, is it on it's not on last week's stuff, it's on this.
Oh, it's just on this section.
Okay.
Yeah, I told you before it was going to be, it's not going to be a log exam. It's really going to be just a glorified quiz. But it's only on this section.
Okay.
So yeah.
Thank
It's
you.
a
Have a
good
good
quiz. All right. Y'all take care and I'll see y'all on you too, Robin. Thank you. I'll see y'all on Friday.
Have a great day.
Thank you.
Thank you. Have a good one.
Okay. You too. Thanks.